Yes. The short answer is yes. It looks like some of Jupiter's moons have huge oceans hidden inside them. And when I say huge, I mean oceans that can contain more water than all of Earth's oceans combined. This isn't a wild guess. It's based on decades of data from spacecraft that have flown past these weird frozen worlds. This discovery has completely changed how we think about where life might exist in the universe. It's one of the most exciting things happening in science right now. To understand how this is even possible, you have to start with Jupiter itself. Jupiter is a monster. It's more than twice as massive as all the other planets in our solar system put together. Its gravity is immense. Anything that gets close to it gets pulled and squeezed in a serious way. This is the key to the whole story. 4 of Jupiter's moons are special. They're called the Galilean moons because Galileo Galilei first saw them with his little telescope back in 1610. Their names are Io, Europa, Ganymede, and Callisto. They orbit Jupiter in a kind of cosmic dance. And it's this dance, orchestrated by Jupiter's powerful gravity, that creates the conditions for hidden oceans. The force behind it all is something called tidal heating. You know how our moon's gravity pulls on Earth's oceans, creating tides? Now imagine that, but on a much, much bigger scale. Jupiter pulls on its moons, but the moons aren't in perfectly circular orbits. They get closer to Jupiter, then farther away, and they also pull on each other, which keeps their orbits slightly wobbly and elliptical, not perfect circles. As a moon gets closer to Jupiter, the planet's gravity stretches it. The side of the moon facing Jupiter gets pulled harder than the far side. The moon gets deformed, elongated. Then, as it moves farther away in its orbit, the pull weakens and the moon relaxes back into a more spherical shape. This happens over and over on every single orbit. Think about bending a metal paperclip back and forth. What happens? It gets hot. The friction inside the metal generates heat. The same thing is happening to Jupiter's moons. This constant stretching and squeezing creates friction deep inside their cores. It generates a tremendous amount of heat. This internal heat is what can keep water liquid, even in the freezing cold depths of the outer solar system, so far from the sun. It's a planetary scale engine that runs on gravity. Let's look at the moons themselves, because they each tell a different part of the story. The best place to start is with the most extreme example of this tidal heating Io. Io is the innermost of the 4 big moons. It's the closest to Jupiter, so it gets squeezed the most. And Io is not a quiet, icy world. It is the most volcanically active body in the entire solar system. It's covered in hundreds of volcanoes that are constantly erupting, spewing sulfur and lava miles into space. The surface is a chaotic mess of yellows, reds, and blacks. It's a vision of hell. Io is so hot inside that it likely has a global ocean of molten rock, of magma. It's being cooked from the inside out by Jupiter's gravity. Io doesn't have a water ocean. It's too hot and has lost any water it might have once had. But it's the perfect proof of concept. It shows us that tidal heating is a real and incredibly powerful force. It can melt the inside of a world. Now, if you take that same force and apply it to a moon that's made of rock and a lot of ice, you get something very different. You get a potential ocean of water. And that brings us to Europa. Europa is the one everyone gets excited about. It's the second major moon out from Jupiter. From a distance, it looks like a smooth white cue ball cracked all over like an old eggshell. It is one of the smoothest objects in the solar system. It has very few impact craters. So craters are like wrinkles on a planet's face. A lot of craters means the surface is old and hasn't changed in a long time. A smooth surface, like Europa's, means the surface is young. Something is constantly erasing the craters. It's like a Zamboni smoothing over the ice on a skating rink. What could be doing that? A warm, slushy ice layer, or perhaps a liquid water ocean just beneath the ice shell, is the best explanation. The idea is that Europa has a rocky core, surrounded by a massive ocean of liquid saltwater, which is in turn covered by a shell of solid ice that might be 10 to 15 miles thick. The evidence for this ocean is very strong. When NASA's Galileo spacecraft flew by Europa in the 1990s, it carried an instrument called a magnetometer. It measured magnetic fields. Jupiter has a huge, powerful magnetic field. As Europa orbits through this field, the field washes over the moon. The data from Galileo showed something strange. Europa had its own weak magnetic field, but it wasn't a permanent one like Earth's, which is generated by its core. Europa's magnetic field was changing. It flipped its direction in perfect sync with Jupiter's rotating magnetic field. This is a huge clue. The best way to explain it is if there's a layer of something electrically conductive inside Europa. And a global ocean of salty water is a great conductor. The theory goes like this: Jupiter's magnetic field passes through Europa. This moving magnetic field creates electrical currents inside the salty ocean. These electrical currents, in turn, generate their own magnetic field. This is called an induced magnetic field. The data from Galileo was a near-perfect match for what you'd expect from a salty ocean about 60 miles deep. That's an ocean that would contain 2 to 3 times the amount of water as all of Earth's oceans combined. There's more. The surface of Europa is covered in long reddish-brown cracks and streaks. Scientists think these are places where the ice shell has fractured. Water from the ocean below may have welled up, carrying minerals and salts with it. When this material is exposed to the harsh radiation around Jupiter, it changes color, creating those reddish stains. We don't know for sure what the reddish stuff is, but salts like magnesium sulfate are a good candidate. These are the kinds of salts you'd expect to find in an ocean that is in direct contact with a rocky seafloor. And then there are the plumes. In recent years, the Hubble Space Telescope has seen what look like giant geysers of water vapor erupting from Europa's south polar region. These plumes seem to be shooting hundreds of miles into space. If these observations are confirmed, it would be a smoking gun. It would mean that there are pathways for water from the hidden ocean to get all the way out to the surface and into space. It would be direct evidence that the ocean is there and that it's active. So for Europa, the case is very compelling. A young surface, an induced magnetic field, strange surface chemistry, and possible water plumes all point to a vast, dark ocean hidden beneath the ice. Next out from Jupiter is Ganymede. Ganymede is the largest moon in the solar system. It's bigger than the planet Mercury, and it's a strange world, a mix of old and new. Parts of its surface are dark and heavily cratered, which means they are ancient. Other parts are brighter and covered in long, parallel grooves and ridges, which suggests the surface has been pulled apart and resurfaced at some point. It's a world with a complex history. Ganymede also has something unique. It's the only moon in the solar system that generates its own permanent magnetic field, like a miniature version of Earth's. This is a big deal. A magnetic field like this is usually generated by a convecting molten metal core. So we know Ganymede has a hot, active interior, but the Galileo spacecraft found something else. On top of Ganymede's own internal magnetic field, it also showed signs of a second induced magnetic field just like Europa's. This was the telltale sign of a saltwater ocean. The data suggests Ganymede also has a huge subsurface ocean. Ganymede's internal structure is probably more complex than Europa's. The leading model suggests it's like a club sandwich. It has a metallic core at the center, then a layer of rock, then a deep ocean of liquid water. But unlike Europa, this ocean might be sandwiched between layers of ice. There might be a layer of liquid water on top of the rock, but then a layer of a high-pressure, dense form of ice, then another layer of liquid water, and finally the surface ice shell we see. The idea of an ocean trapped between ice layers is fascinating. It has different implications for life than an ocean in direct contact with a rocky seafloor. So, Ganymede, the giant moon, almost certainly has a giant ocean. It's just buried deeper and might have a more complicated structure than Europa's. The last of the 4 big moons is Callisto. Callisto is the farthest out. It orbits beyond Jupiter's main radiation belts. For a long time, scientists thought of Callisto as the boring one. Its surface is the oldest and most heavily cratered in the solar system. It looks like it hasn't changed much in billions of years. It's just been sitting there, getting pummeled by asteroids and comets. It shows no signs of volcanic activity or plate tectonics like the other moons. It seemed like a dead world. Because it's farther from Jupiter, the tidal heating effect is much weaker on Callisto. It doesn't get stretched and squeezed nearly as much as Io or Europa, so for a long time nobody expected to find an ocean there. But then the Galileo magnetometer took a look, and just like with Europa and Ganymede, it found the faint but unmistakable signature of an induced magnetic field. This was a shock. The data suggested that even Callisto, this ancient, quiet-looking world, might have a layer of salty liquid water deep beneath its crust. The ocean inside Callisto would be different. Because there's less tidal heating, it would need something else to help it stay liquid. Scientists think the water might be mixed with ammonia or other natural antifreeze compounds. It'd be very deep, maybe 60 miles or more beneath the surface. Crucially, it's probably sitting on top of a core that is a mix of ice and rock, not a neat separate rocky core like Europa might have. This means the water might not be directly interacting with rock silicates, which could limit the chemical reactions available for potential life. So we have a spectrum. Io is all fire and molten rock. Europa is the top candidate for a habitable ocean in contact with a rocky floor. Ganymede has a massive, complex ocean probably layered between ice, and even ancient Callisto seems to be hiding a deep, dark ocean of its own. Jupiter's gravity is a powerful enough engine to create and sustain liquid water in 4 very different worlds. This brings us to the big question. So what? Why does it matter if there are oceans locked away inside these frozen moons? It matters because of the search for life. For most of human history, we've assumed that life needs to be on a planet like Earth, a rocky world at just the right distance from its star for liquid water to exist on the surface. This is called the habitable zone, or the Goldilocks zone. Not too hot, not too cold. These moons change everything. They show us that you don't need to be close to a star. You don't need sunlight. You can have a perfectly good ocean of liquid water in the cold, dark outer reaches of a solar system, as long as you have a source of energy. And for these moons, that energy comes from gravity, from tidal heating. This dramatically expands the number of places where life could potentially exist, not just in our solar system, but across the galaxy. The habitable zone concept needs an update. There could be habitable moons orbiting giant planets far from their stars. So, could there actually be life in these oceans? We don't know. But they seem to have the 3 key ingredients that scientists think are necessary for life as we know it. First, you need liquid water. We've just seen that Europa, Ganymede, and Callisto likely have that in abundance. Check. Second, you need a source of energy. Life needs energy to carry out its basic functions. On Earth, most life gets its energy from the sun through photosynthesis, but that's not going to work under a thick shell of ice. However, tidal heating provides energy in the form of heat. But there's another, more exciting possibility. Here on Earth, deep on the ocean floor, far from any sunlight, we've discovered thriving ecosystems. They cluster around hydrothermal vents. These are cracks in the seafloor where superheated mineral-rich water from the Earth's interior gushes out. The life there doesn't use sunlight. It uses chemical energy. Bacteria and other microbes feed on the chemicals coming from the vents, a process called chemosynthesis. And then other animals like tube worms and crabs eat those microbes. Could something similar be happening on the seafloor of Europa? If Europa's ocean is in direct contact with its rocky core, and if tidal heating is flexing that core, it's very plausible that there are hydrothermal vents down there. These vents could provide a steady source of heat and chemical energy for life to emerge and survive in the total darkness. This is why Europa is such a prime target. Its ocean seems to have the right setup. Third, you need the right chemical building blocks. Life on Earth is built from a handful of key elements, especially carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Are these elements present in Jupiter's moons? Almost certainly. The moons were formed from the same cloud of gas and dust that formed the rest of the solar system. Comets and asteroids, which are rich in these organic compounds, have also been crashing into them for billions of years, delivering these raw materials. The reddish stains on Europa's surface might even be some of these complex chemicals churned up from the ocean below. The raw materials for life are likely there. So Europa in particular seems to have all the necessary ingredients: water, energy, and chemistry. It doesn't mean life is there. It just means it's a possibility we have to take seriously. Life could be swimming in that dark ocean right now. It could be microbial, it could be something more complex. We have no idea. This is all based on data from older missions that were, for the most part, just flying by. To get real answers, we need to go back with instruments specifically designed to study these oceans. And that's exactly what's happening. There are 2 major new missions on their way to Jupiter's system. The first is the European Space Agency's JUICE mission, which stands for Jupiter Icy Moons Explorer. It launched in 2023. It will perform a long tour of the Jupiter system, doing multiple flybys of Europa and Callisto. But its main target is Ganymede. It will eventually become the first spacecraft to ever orbit a moon other than our own. It will orbit Ganymede for months. Its goal is to characterize these oceans in detail. It has ice-penetrating radar to try and measure the thickness of the ice shells. It has advanced instruments to map the magnetic fields and gravity of the moons, which will give us a much clearer picture of what their interiors look like. It will study their surfaces to understand their geology and composition. JUICE will give us our best look yet at Ganymede and Callisto. The second mission is NASA's Europa Clipper. This spacecraft is scheduled to launch in 2024. As its name suggests, its focus is entirely on Europa. It won't orbit Europa directly because the radiation environment there is incredibly intense and would fry the spacecraft's electronics. Instead, it will be in a long looping orbit around Jupiter that allows it to perform dozens of close flybys of Europa, some as low as 16 miles above the surface. Europa Clipper is a powerhouse. It carries a suite of 9 advanced scientific instruments. It has radar to map the ice shell and look for pockets of water, or even the ocean itself. It has magnetometers to confirm and precisely measure the induced magnetic field, which will tell us the ocean's depth and saltiness. It has cameras to map the surface in high resolution and spectrometers to figure out what that reddish stuff on the surface is actually made of. And most excitingly, it has instruments designed to fly through any plumes of water vapor that might be erupting from the surface. If it can fly through a plume and sample it directly, it could analyze the composition of the water from the ocean without ever having to land or drill through the ice. It could look for salts, organic molecules, and other signs of a habitable environment. It might even be able to detect biosignatures, which are chemical signs of life. This would be a monumental discovery. These missions will not be able to definitively find life. They aren't designed for that, but they will be able to tell us for sure if these oceans exist. They will be able to characterize them. They will tell us if the conditions there are truly habitable. They will lay the groundwork for future missions that might one day land on the ice, and maybe even send a robotic submarine down into the dark, alien waters of another world. So, are there oceans inside Jupiter's moons? The evidence we have right now points overwhelmingly to yes. Not just small pockets of water, but global oceans that dwarf our own. These discoveries have forced us to rethink our place in the universe. Life might not be a rare miracle confined to sunlit surfaces. It might be a common phenomenon, hiding in the dark, powered by the patient, relentless pull of gravity. The answers are waiting for us out there, in the cold and the dark, orbiting a giant planet. And we are on our way to find them.